Now we look at compound inequalities. Here I have 8 examples of compound inequalities. So here compound means that we have more than one inequality. For example, in the first case, we have x greater than or equal to 3 and x greater than or equal to 5. So there are 2 inequalities joined by a word and. And the second example is very similar to the first one, 2 inequalities, exact the same, but the joining word is or. And similarly, in the third example, the inequality signs are flipped. Greater than becomes less than, and with 2 different joining words. And in these examples, we have different opposite inequality signs. One of them is greater than, the other one is less than. So let's look at these 8 different cases. So for compound inequalities, it means that there are 2 inequalities we got to consider. So in the first case, x is a number that is greater than or equal to 3. And the second case, x is the second inequality says x is greater than or equal to 5. And in real life, sometimes we don't distinguish between the word and the word or, but in mathematics they are different. So and means both, which means we got to satisfy both requirements. Or means you don't have to satisfy. Yes, you can satisfy both requirements, but you don't have to. You may just meet one of the requirements. So let's look at how to find the solution of a compound inequality. So we got to satisfy, in the first case, we got to satisfy both inequalities. Drawing the graph will help us better do the problems. So for example, I'm going to first find the numbers greater than or equal to 3. So 3, that's 3, 5. All the numbers greater than or equal to 3 will be starting from 3, closed because we do have an equal sign, and raise the line and it goes to the right. Now let me change the color because we do want to draw, because this is one problem. It looks like 2 inequalities, but they're joined by a word and. So this is one problem. You don't want to draw two graphs for one problem. So we're gonna draw the graph for x greater than or equal to 5 on the same number line. We start from 5 and closed again, and greater than or equal to 5. So still it's gonna go to the right. So I make the line a little lower so we can distinguish them. Okay, so now let's look at the graph. So what numbers will meet both requirements, which means will fall. And we know that the numbers under each line meet each requirement. For example, these numbers on the right side of 3, they fall under the blue line. That means they meet the first inequality. And the numbers fall under the red line. Maybe I can highlight with the red color. So these numbers in red, they meet the requirement of second inequality. Since we want the numbers to meet both, of course, and these will be the final answer. So when we have 2 lines, 2 graphs on one number line, we do need you to shade the area to show which ones are the final answer. So these numbers here don't meet the requirements of both. And if you think without drawing the graph, you might be able to understand this, because any number greater than 5 must be greater than 3. So if you have a number greater than or equal to 5, that satisfies the second inequality. Of course, it's going to satisfy the first inequality. Definitely, it's going to be greater than or equal to 3, but not vice versa. For example, we have numbers here between 3 and 5. They are bigger than 3, so which means they satisfy the first inequality, a number greater than 3 may not be greater than 5. So like these numbers here, they don't satisfy the second inequality. So these cannot be the solution of the compound inequality. So with these two together, although you see 2, but it's one problem. So for this compound inequality, the solutions will be the numbers greater than or equal to 5. Graphically, it's the shaded numbers, or the numbers in red. So we're going to use interval notation to describe it. Bracket for 5 because 5 is included. Comma in infinity to indicate the number goes on forever. So any number between 5 and infinity. So any number greater than or equal to 5, in other words, so will be the solution. Okay, let's look at the second case. If we change the word from and to or, does it make difference? So again, in real life, sometimes we think they're the same, but in mathematics, and or, they're different. Or means you can just meet one of the requirements. You don't have to meet both requirements. Okay, we're still going to draw the graph to help us understand this. So first I'm going to draw the number line for x greater than or equal to 3 on the right side. And secondly, I'm going to use the red color to draw the numbers that can meet the second requirement, the second inequality. So now when we look at them, so this time we're not looking for numbers that meet both requirements. We're looking for the numbers that meet one of the requirements. As you can see, all the numbers, let me use them to shade all the numbers. So for example, all the numbers that are on the right side of 3, all of these numbers on the right side of 3, they satisfy the first inequality. So of course, it's going to be solutions of the whole compound inequality, because or means if you meet one requirement, then it's good enough. You don't have to meet the other requirement. So even those numbers right here between 3 and 5, although they are smaller than 3, they are still going to be the solutions of this compound inequality, because these numbers meet the first requirement. It doesn't have to meet the second requirement. It's just like in real life, for example, you may have sometimes we say, okay, you can be a senior or a toddler to get a discount. So if you are a toddler, you don't have to be a senior. You will get discount. If you're a senior, you don't have to be a toddler to get discount. So it just means we only need meet one of the requirements. That's good enough. And these numbers here, under 5, under the red line, they not only meet the requirement of second inequality, but also the first, which is even better. Of course, these are all solutions. So the final solution will be all the ones we shaded, including these ones. So you can compare the graphs and you can see if we have a word and, you cannot pick numbers between 3 and 5. And of course, not here either. But if we change it to or, these numbers will also work. They don't have to be greater than 5. They are greater than 3. That's good enough. So that solution will be numbers on the right side of 3. So we use interval notation to describe it, will be bracket 3 and comma infinity to describe all these numbers here. Okay, what if we have less than? Well, the less than case is very similar to greater than. The only difference will be we're having the lines to, when we have the lines go left, because less than, and let me go ahead and just do the last two together. The lines will go to the left. And now we're going to draw 5. Less than will go to the left. And less than will go to the left. Okay, so for and case, remember we got to meet both requirements. As we can see, only numbers from 3 to negative infinity, these are going to be meeting the both requirements, because any number smaller than 3, of course, is going to be smaller than 5, but not vice versa. So that's why we cannot take these numbers, because they are not smaller than 3. They're bigger than 3. Okay, so the answer would be negative infinity to 3, the bracket. And similarly, for the last case, similar to the second example we had, for OR, we don't need to meet both requirements anymore. We just need to meet one of the requirements. So all the numbers, I do need to shade them. If it's hard for you to highlight, then you can shade them. So all the numbers on the left side of 5, they're smaller than 5. Then these are going to be solutions, because OR means if a number is meeting one of the requirements, it's going to be the solution. So it's already including all the answers of the first one. And so that's negative infinity to 5. Okay, so usually when you have an OR, because you don't have to meet both, the requirement is more relaxed than not as strict as AND. So you have more solutions, as you can see. When you have AND, since you want to meet both requirements, usually you have less solutions. Compared to, when you compare the first case and second case, more solutions, less solutions, and more for OR, less for AND. Now, let's look at the other cases. What if one of them is positive, greater than, the other is less than? So we're still going to draw the graphs to show. In the first case, x is greater than or equal to 3. So close the dot and go to the right. In the second inequality, we have x less than equal to 5, which means we got to make the line go left. And means we got to find numbers that meet both requirements. So when numbers are greater than or equal to 3 and less than or equal to 5, as you can see from the graph, only these numbers are under both lines. So these numbers are under the red line, which means they are smaller than 3. So this is indicated by red and this is by blue lines. And these numbers are also under blue line, which means they meet the first requirement. So they meet both requirements. So we're looking for the intersection here. But for the OR case, by the way, the interval notation will be 3, 5. A range from the numbers from 3 to 5, including 3 and including 5. So in this case, in the next case, when we change it to OR, we don't need to look for the intersection. We look for numbers under one line. Although the graphs look exactly the same, the final answer will be different, because first of all, I'm going to shade all the numbers under the red line. These are numbers. So these should be solutions, because meet one of them. And then I'm going to shade the numbers under the red line, and then these are under the blue line, and then these are also solutions. As we can see, it's every number is shaded now. So the solution will be from negative infinity to positive infinity. Every number will meet the requirement. So either meet first one or meet the second one. Now next, for the last two cases, x is less than or equal to 3, so the line goes to the left. X is greater than or equal to 5, the line goes to the right. So for the bottom, it's the same, except the joining word is different. But in number 7, we are looking for the numbers less than 3 and greater than 5. They don't exist because we cannot find numbers that are under both blue and red lines. Or in other words, you cannot find a number that's smaller than 3 but also bigger than 5. It's impossible. So you will just write down, we cannot find any intersection. So let's write down no solution. But for the number 8, since it says you don't have, or means you just need to be one of them, one or the other. It doesn't need to be both. So in this case, we got solutions here. These are going to be solutions, or here. So just like toddlers or senior, they are both qualified. So in this case, the solution will have two separate parts. The first part will be from negative infinity to 3. And the second part will be from 5 to positive infinity.